Yep, there.
Okay.
I also emailed you the document.
All right. Number one, hold on a minute. I was going to say, this Windows version 10 has a lot to be improved upon. It's not perfect
Yeah.
by any means. So the graph they're showing you is sine x minus x over x. So if you look at the graph, what's the limit as we approach 0 from the plus side?
Looks like it's infinite.
No, hold on. Look at this graph right here. We're on the x-axis. We're approaching 0 from the right. What's
Yes.
the y value that we're headed towards?
0.
Correct. Now let's solve it algebraically. Why that's 0. Sine of x minus x over x, I can break that into two fractions, right?
Mm-hmm.
The sine of x over x minus x over x. What's the limit of that as x goes to 0? It's 1.
Negative infinity.
It's 1. In other words, yeah, one of the things they have to tell you, because you don't have enough calculus to know it yet, or to solve for it, is the limit of sine of x over x as x goes to 0 is 1. And that's just something you have to memorize at this point.
Okay.
Okay? So this problem becomes x over x is 1. So what is the limit of sine of x over x minus 1 as x goes to 0? What should it be?
Should it be, so as x is going to 0, would it be 1?
Well, that goes to 1, but I'm subtracting 1. So it's got to be 0.
Okay.
This is 1, okay? But we have 1 minus 1, so that's why we have 0. And that agrees with our graph. In other words, you should always be able to do this two ways. You should always be able to look at the graph and answer this kind of a question, but you should also be able to do it algebraically. And I did it both ways.
Okay.
Okay. Let's look at number 2. I assume you just want to go through these in order?
Yes.
Okay. And this time as x goes to 0. Well, what's the graph tell us? What's the limit from the right?
From the right, it goes to 0.
What's the limit from the left?
It goes to 0 as well.
So
So they're the same.
So what is the limit?
0.
Now, doing it algebraically, they don't really insist that you do it algebraically, do they?
No.
They just want you to be able to read the graph and figure it out.
Yes.
I could do it algebraically, but here's what happens. It's 2x squared over x whenever x is greater than 0. And it's 2x squared over minus x whenever x is less than 0. Well, this one, the x's cancel out. And as x goes to 0, clearly it's going to go to 0. And this one, the x's cancel out, and 2x over or minus 2x goes to 0 as x goes to 0. So we can do this one algebraically as a piecewise function, but we have to set it up. Whenever you have absolute value, it's always going to be a piecewise function. Hold on 1 minute.
Okay.
All right. I guess we don't really need to do these algebraically. Let's just go through the graphs. Boy, I kind of hate that, but well, what's this limit as we approach 3 from the left side?
3 from the left side?
Yeah, looking at the graph only.
Looks like it's headed towards infinity.
Okay, there's a problem here, and let's go over it. When I say, what's the limit as we approach 3 from the left side? Well, here's 3. And what I'm doing is I'm hopping aboard this function, and I'm going to approach it from the left side. So what is that point right there on the f of x axis?
1.
That's what it is then. You understand? In other words,
yeah.
Whatever this is down here where it says x approaches 3 from the left, you get on the x-axis, and you approach 3 from the left side, which is exactly what I did. I was totally unconcerned with the y-axis. I just got on the function and I started approaching the value of x equal 3 from the left side. Well, clearly that's 1 from our picture. Okay. And just to do the algebra, the top factors into x minus 3 times x minus 2 all over x minus 3. We would cancel those. We would be left with x minus 2. What's the limit of that as x goes to 3? 1. So algebraically it agrees with...
Yeah.
What's that?
No, I said yes.
Yeah. But the other concept is really important, and it looked like you were missing it a little bit. Well, it's not messing up. I mean, limits are hard. Compared to any other math you've ever had, limits are different. So you got to kind of get used to it. Okay, so let's look at number 4. In fact, let's just do the graphs from here forward. There's a reason they want you to estimate these limits graphically. And now that I look at the instructions, estimating limits graphically, not algebraically. So let's just do them graphically. What's this limit as I approach negative 2?
Negative 2. 0.
What is it from the left?
It looks like it would be touching 0 once it hits negative 2.
No, here's negative 2 right here. Can you see my cursor?
Oh, so negative 1.
Correct. From the left. What is it as we approach negative 2 from the right?
It would be 1.
Correct. Since they are not the same, what is the limit at negative 2?
Undefined.
Does not exist. Not quite undefined. Undefined has a different meaning. Undefined is generally interchangeable with infinity. In other words, if I say, what is the slope of a vertical line, they'll tell you it's undefined, but it's actually infinite. It's an infinite slope. Okay, so undefined and infinity tend to mean the same thing, but does not exist means it does not exist. It's not infinite. It does not exist because in order for a limit to exist, it has to be the same when approached from the left as when approached from the right. So whenever you see a discontinuity like this, a jump discontinuity, you can tell that the limit from the left is not going to be the same as the limit from the right. So the limit never exists at a discontinuity like that.
Okay.
Look at number 5, looking at just the graph. What's the limit as we approach 0 from the left, which is the only direction we can approach it from?
It will be -1, -2, -3, -4, -5, -6, -7, -7.
Correct. And that is a legitimate response. But that's the only thing that's legitimate. I could not tell you what the limit was as we approach 0.
There isn't another line.
Right. So you can only approach 0 from the left.
So would it be -7 period?
Well, no, I don't know, to be honest. I probably shouldn't have even postulated that. I don't think you'd ever get the question is, what is the limit as we approach 0?
Okay.
The question only makes sense is, what is the limit as we approach 0 from the left side, because we cannot approach it from the right side.
Okay.
It wouldn't really make sense to say, what is the limit as we approach 0?
Yeah, that'd be better.
About number 6. What's the limit as we approach 4 from the right? What is it?
No, I'm saying from the right side.
Mm-hmm.
1, 2, 3, 4, 5, 6, 7. 7.
Okay. How about, that's all they want to know. Okay. That's proper answer.
Okay.
What's the limit as we approach 0 on number 7?
There's only one, and that's -3.
Correct. It's -3 because when we approach 0 from the left, it's -3, and when we approach 0 from the right, it's -3. Since both are the same number, the limit does exist, and it's -3.
True. Correct.
8. What's the limit of, let's see, it's the blue function is when x is less than 0. The red function is when x is greater than 0. So what is the limit at x equal 0?
Would it be 0?
Yeah, I mean, yes, it is.
This is weird.
Well, but still, the only way to answer it is, what is it from the left? 0. What is it from the right? 0. Therefore, the limit at 0 is 0.
Okay.
Let's look at 9.
It would be, does not exist.
Correct. Notice that if we look at the blue line only, the limit is different from the left than the right because there's a jump discontinuity there.
True.
So it's not going to exist at 0 from the blue lines. And if you look at the two red lines, which must account for this, it's also not the same from the right as the left. So regardless of whether you're looking at the blue or the red, not quite sure what they mean here. The red usually means an imaginary. That's the imaginary solution. And yeah, I'm a little confused as to why they have red and blue. I guess the blue is the real solution, the red is the imaginary solution. But in either case, the blues have a jump discontinuity, the reds have a jump discontinuity. That limit doesn't exist.
She said this was from her calculator.
This is?
Yeah, these graphs were from her calculator.
Well, if I go in the Wolfram Alpha and I put functions in, it gives me the imaginary results also. Notice that x squared plus 5. Let's look at that function for a moment. That's what it's equal whenever x is greater than or equal to 0. Well, x squared plus 5 is that part of the parabola. In other words, if I wanted to graph that parabola, it would look like this. Notice that red line is just the right part of it.
True.
And if I look at the top one, x minus 5, that's the blue. So if I was only going to use one graph to graph this function, I would graph this blue to the left, and I would graph that red to the right. So the limit does not exist at 0 if I'm comparing that blue line with that red line because of that big jump discontinuity. Now what the other red and the other blue is, I'm not real sure. I really don't know what the other red or the other blue is. That's y equals 0. I'm not sure why they have it in red and why they have it in blue.
She said that was an accident.
Yeah, it's a little confusing. I don't quite get it. But if that's what she said, then that's probably true. Okay, let's look at 10. As we approach negative 4, which is 1, 2, 3, 4, what's the limit from the left?
Okay, 1, 2, 3, 4. Would it be does not exist?
No. What is it from the left? Jump on top of the function and start drawing arrows as you approach 4 from the left. And by that, here's what I mean. This is truly the way to do it. If you want to understand limits, this is the best way I know how to do it.
It looks like it's in the middle of the two functions.
Well, correct. What is in the middle of those two functions? That's a vertical asymptote.
True.
Well, if I hop on the function and I start drawing arrows as I'm approaching minus 4 from the left, where am I headed?
To negative infinity.
Correct. Now let's approach it from the right. Where am I headed?
Negative infinity.
What is the limit at negative
infinity?
Negative infinity, exactly. And this is a case where I don't think you want to say you certainly don't want to say it doesn't exist, because it does exist. If the limit from the left is the same as the limit from the right, it exists.
True.
Okay, and you wouldn't want to say undefined, because undefined does not distinguish between positive infinity and negative infinity. So using the word infinity is actually very descriptive here.
Okay.
What is the limit? Negative infinity. But number 11. As we approach 4 from the left, what is it?
Negative infinity.
What is it from the right?
Infinity.
That limit does not exist.
Correct.
Because they're not the same. It doesn't matter whether infinity is in there or not. If they're not the same, the limit does not exist. Now number 12. As x goes to infinity, what happens to e to the 2x minus 5?
It goes to infinity?
Yeah, exactly. And you would expect it to. If I say e to the infinite power, well, that's infinity.
True.
How about number 13?
It looks like they're the same one.
No, not quite. This one is we're approaching negative infinity.
Oh, you're right. Would that be 0?
Yes. And you can do it just exactly the way I've been doing it. Start putting arrows headed left. Where is the y value headed? 0. And that makes sense if you think about it. Because basically what this function is, if I said e to the minus infinity, that's the same thing as 1 over e to the plus infinity. Well, if the denominator blows up, then the whole thing's going to 0.
Okay.
If I have 1 over infinity, the limit of that is 0. The denominator blows up, it goes to 0. If the numerator blows up, it goes to infinity.
Okay.
Kind of actually like the way they're doing this. Give you this many problems that are just estimating it based on the graph is really a good idea. And not worrying about the algebraic limit at the moment. So as I'm approaching 6, you can probably figure out that 6 has to be that grid mark right there. I approach from the left, what is it?
It will be infinity.
And from the right?
Infinity. So it's infinity.
Yep. And notice what happens. As I'm approaching 6, I've got 5 divided by 6 minus 6. That's the same as 5 over 0. Well, that's infinity. When you're dividing a number by 0, you know, the one thing you cannot do in mathematics is divide by 0, but the truth of the matter is that when you divide a number by 0, you get an infinite answer. And if you don't believe it, take that number and divide it by 1. That's equal to 5, right?
Yes.
Now divide it by 0.1. That's equal to 50. Now divide it by 0.01. That's equal to 500. As the denominator gets closer and closer to 0, the answer gets bigger and bigger and bigger. So when you are dividing by 0, you're really talking about infinity. Not really undefined. I hate the word undefined because it can mean a lot of different things.
True.
Number 15.
Okay. So to infinity.
As x goes to infinity, what does the function do?
0.
Yep. Again, just hop on the function, start drawing your arrows towards infinity, and I can tell that I'm not going anywhere off that x-axis. But
True.
why is it? If I have x squared over 4x cubed, notice the x squareds go away and I end up with 1 over 4x. Well, as x goes to infinity, again, I've got 1 over infinity. That's going to 0. So
True.
I can look at it algebraically. They want you to look at it graphically, but you can also always make algebraic sense of it. And notice that the degree in the denominator is bigger than the degree in the numerator. When they talk about the limit as x goes to infinity, that's the same thing as saying what is the right-hand end behavior of this function. If I say what is the left-hand end behavior, then I'm talking about when x goes to negative infinity.
True.
Either way, this thing goes to 0. And it's because the denominator has a higher power than the numerator. That means, in other words, whenever you're talking about end behavior, the only thing you care about is the highest degree in both numerator and denominator. So I didn't count this x minus 22 or the minus 13. I only looked at x squared over 4x cubed because that's all I need to look at when I'm talking end behavior. And that reduces to 1 over 4x, which clearly goes to 0 as x goes to infinity.
Okay.
I'm giving you a little bit of the algebraic solutions here, but as long as you are getting the visual, graphical solutions, then I know you're getting it. What happens here is I go to negative infinity.
It's
hard to see, huh?
Yeah, it looks like it starts to stop declining as much as it goes down further.
Yeah, the answer is 1/3. How did we get it? Yeah, on this one we kind of need to look at the algebraic solution.
True.
And I'll tell you why. In other words, if we're looking at end behavior, we are, because it's got x going to negative infinity, and the degree in my numerator is 1, the degree in my denominator is 1, if they're the same, then the end behavior is the ratio of the coefficients, always, even if it was x squared and x squared. If they're the same exponent, then the end behavior, the limit as x goes to infinity, is that ratio of coefficients. So it's 3/9 or 1/3. And that's what that horizontal asymptote is at, is 1/3. You'll notice that it's not on the x-axis. It's above the x-axis for both right and left. In other words, the end behavior as x goes to negative infinity is 1/3. The end behavior as x goes to positive infinity is 1/3.
Okay. That's weird. Like, how would I identify that in the future?
What's that?
How would I identify that, like, ahead of time in the future?
You need to be able to do the algebraic. Here, let me give you another algebraic problem.
Okay.
What's the limit of that as x goes to infinity?
1/2?
Yep. That's all you need to know.
Okay.
As x goes to negative infinity, still 1/2. Especially with the even power, because negative infinity squared becomes positive infinity.
Okay.
Okay. And 17. Looking at this curve, it's a little hard to see what's going on because it's not a straight parabola. There's a little humps and bumps going on down there. But if you were to blow that thing up, you could kind of see what it is. But more importantly, let's look at it algebraically. In other words, the way they've drawn it here at this scale, I can't see. Let's see if I can blow it up a little bit. Maybe I can see it. Okay, yeah, I can see it at a better scale here. Notice that it actually goes below the x-axis. And then what does it look like the limit is as x goes to 0?
It looks like it's 0.
Yeah, right there. It does look like it's 0. And I'm quite certain that that's the answer. But let's see if we can figure out more about it by looking at it algebraically.
Okay.
Cox? They mean cosine?
I have no idea where that came from.
It has to be cosine.
Probably cosine of x.
Well, there's no mathematical expression that's COX. There's this cosine. That's the hyperbolic cosine, but there's nothing else. Well, if we look at this limit as x goes to 0, clearly that part goes to 0. This part goes to infinity, right? I got a number being divided by 0. The problem is what is the cosine of infinity? And the cosine curve looks like this. What's the cosine as x goes to infinity?
Cosine when it goes to infinity?
No. What's the cosine of 1/x? Well, yeah. No, what's the cosine of x as x goes to infinity? Looking at my curve.
Infinity?
No. It bounces back and forth between 1 and -1, right?
So,
In other words, this is 2 pi, that's 4 pi, that's 6 pi. As x goes to infinity, I don't have a limit. When you have an oscillating function, it's somewhere between 1 and -1, but I don't know where. But the fact is that I'm multiplying this thing by x squared, which goes to 0. So it doesn't matter whether that is between 1 and -1. We know that this part is going to always be between 1 and -1 as we get big. True. But this part here definitely goes to 0. And if you multiply 0 by some number that's between 1 and -1, you get 0. So that limit is definitely 0. But the limit of just this part here doesn't really exist. I mean, you can't put a number on it. And in fact, they would say it does not exist. Because it doesn't, nor does the sine of x. In other words, what's the limit of the sine of x as x goes to infinity? Well, the sine curve looks very similar. It just goes up and down, up and down, up and down. So as x goes to infinity on the right, heads to the right, what does the sine of x do? It goes up and down every 2 pi. So it bounces back and forth between 1 and -1, meaning it doesn't go to a specific number. So that would be does not exist. And
okay.
of sine of 1 over x, it's not really any different. Yes, it is. Excuse me. Is the limit of sine of 1 over x as x goes to infinity, it's going to be 0.
Okay.
This is not the curve for sine of 1 over x. This is the curve for sine of x. But the only reason I know it goes to 0 is because I know the sine of 0 is 0. And if x is going to infinity, this 1 over x is going to 0. So the limit of the sine of 0 is definitely 0 right there.
Okay.
But from a graphical perspective, clearly this is 0. Because all we have to do is blow it up. I mean, assuming they give us an accurate graph, we can tell that that thing, it's negative between 0 and -1, and it's negative between 0 and 1. But as we head to 0, it's 0.
True.
Hold on, I just want to make sure that I was looking at. Yeah, okay. Yeah, it was as x goes to 0, not as x goes to infinity. Okay. Is that all there were? I think we did these. Or maybe not.
Yeah.
Hold on. Is 17 the last one?
Yes.
Yeah, it is. Okay.
I have another one though.
Okay. Go ahead and send it if you want.
Okay, one moment. Okay, since it.
These are actually kind of fun. Once you get used to them on how to do it, they're a piece of cake, right? I mean,
yeah.
You just jump on the graph and point your arrows towards what the x value is pointing towards.
True.
That's all you have to do, really. All right, let's look at. Should we start at 1?
Yes.
Again, we're estimating them with graphs only. So what's number one?
Number one is, 1 second. Okay, number one would be 1.
Okay, number two?
Number 2 would be 3, no, 4.
Number three?
Oh, number 3.
No, you were correct on number two. It's 4.
Oh, okay, you scared me for a second.
That's okay. We get our number 1s, 2s, 3s, and 4s all jumbled together. It's easy to make a mistake. On the question number 3, what's the limit as x goes to 2?
Does not exist.
Okay. Because there's a jump discontinuity, which means the limit from the left is not the same as the limit from the right.
From the right.
About number 4.
Would it be 0? No, it does not exist because it's different.
What's the limit from the left?
From the left, it'll be does not exist.
I can jump on this function and start heading towards the number 2. Where am I pointing to? What y value am I pointing to?
You're pointing towards the 2?
Correct. This 2 right here.
Yes.
Now let's head there from the right. What's the limit from the right?
2.
So the limit from the left is 2, the limit from the right is 2.
What about the whole?
Forget about the whole. What's the limit as we approach 2?
2.
Correct. Does not matter if there's a hole there. Does not matter if f of 2 is actually 0. The fact is that the limit from the left is 2, the limit from the right is 2, therefore the limit is 2.
Okay.
Okay? That's the hardest one to understand for everybody. Because it's hard to put together the fact that the limit can be 2 when f of 2 is equal to 0. In other words, at the number 2, the actual value of the function is 0. So it doesn't seem to make sense that as we approach 2, the limit could be a different number than 0, but it is. Whenever you have a hole and a removable discontinuity. In other words, whether that thing was there or not, this limit is 2.
Okay.
About number 5. As we approach 1 from the left, what is the limit?
4.
From the right,
4.
what's the limit as we approach 1?
4.
Good. Number 6. As we approach 5, what's the limit?
It's on the asymptote.
What is it from the left?
Negative infinity.
What is it from the right?
Infinity. Does
All
not
you
exist.
need to know, does not exist. And in fact, I cannot think of a situation where you have a discontinuity here that would exist. In other words, discontinuities almost always mean that the limit at this number does not exist. Unless I have the following situation, which is if I had y equals 1 over x squared, that's a little different. Because now that looks like this. I still have a vertical asymptote, but the limit from the left as x goes to 0 is positive infinity. The limit from the right is positive infinity, so the limit definitely exists. Even though there's an asymptote there, and there's a discontinuity, an infinite discontinuity, the limit still exists. I would say the limit is infinity, but that might be a bit of a stretch. Mathematicians don't like saying a limit equals infinity. For one thing, it makes it sound like infinity is a number, and it isn't.
True.
concept. Infinity means growth without bound. So it's definitely not a single number.
True.
7. What's the limit as did we do 7?
No, we didn't.
7 and 6 look amazingly similar.
Yeah, they do.
I think they are the same, aren't they?
Yeah, they are the same.
They are. 2 over x minus 5. The graphs certainly look the same. Okay.
Yeah, they are the same.
Well, let's look at 8. It's the limit as we approach 1.
1. Would it be 1?
Look on the x-axis where 1 is.
Yes.
So as we approach that point from the left, where are we headed to on the y-axis?
We're headed down to -1. Or no, just 1.
Just 0.
Or yeah, dang it! I was looking at the 1, and darn it, I was looking at 1, but then
the most difficult thing with interpreting graphs is keeping your x and your y distinct from one another.
True. Yeah, I got confused just now.
A lot of people do. A lot of people do, because I'm not quite sure how to explain it better, but the way I explain it is, get on the curve, approach this number from the left. Well, that's what I'm doing if I'm on the curve. What am I headed for? I'm headed for a y value of 0. And when I approach it from the right, I'm headed for a y value of 0. So the limit has to be 0.
Okay.
Okay. Number 9. This is strange looking.
Yeah, by far.
Whenever you see gigantic close oscillations like this, does not exist.
Yeah, she told us, but does not exist due to oscillation of like the graph or something.
Right. Well, let's examine why that is true. I'm saying that I've got 1 over 0, right? So I'm basically saying, what is the cosine of infinity? Since infinity is not a number but a concept, the cosine of infinity merely fluctuates between -1 and 1. And that's what this thing is doing as we approach 0. Is the cosine is going up and down so fast, it's fluctuating so fast between -1 and 1 that there is no limit as we hit 0, because there's no limit to the cosine of infinity or the sine of infinity. An oscillating function that just keeps going back and forth between two numbers doesn't have a limit. In other words, let's take this function here. -1, 1, -1, 1, -1, 1. If I head to infinity, I'm still going to just have a series of -1s and 1s, -1s and 1s. I'm never going to settle on a particular number. So that limit doesn't exist. Number 10, referring to this graph, what is f of 1?
F of 1 would be 1.
Go to 1 on the x-axis, find the point on the graph that it corresponds to, and read it off the y-axis.
Okay, because from the left I see it at...
Don't look, the limit doesn't exist, because from the left it's like 3.5, from the right it's 1, so the limit doesn't exist. But f of 1 definitely does. There's a black dot right there.
2.
That's f of 1, and it's equal to 2. What is the limit of f of x as we approach 1?
3.5.
From the left, what is it as we approach from the right?
1 does not
Does
exist.
not exist. That's the very first question you'll almost have to always ask yourself, is what is it from the left, what is it from the right? If they are not the same number, it does not exist. Simple as that.
Okay.
What is f of 4?
Does not exist.
Correct. According to this graph, x cannot be 4. What's the limit of the function as we approach 4?
From the left it's 2, and from the right it's 2, so it'll be 2.
Correct. See, once you figure out how to do these, they're really fun because they're easy.
True.
I mean, this one's the only really tough one that we've had. This one's the one that's impossible to tell by looking at the graph because it oscillates so fast that all we have is near vertical lines going up and down.
True.
But these are all easy. You just have to know how to do it. What's f of minus 2?
Does not exist.
What's the limit of f of x as we approach minus 2?
1 second. Cinnamon, stop. Okay, so from the left,
Good.
it's going to negative infinity.
Huh?
Wait, from -2?
Yep. You're right. When you approach -2 from the left, the function goes to negative infinity. What do you
when it comes
approach
to right,
-2 from the right?
Infinity.
So?
It does not exist.
Correct. What's f of 0?
F of 0 would be 4.
What's the limit of f of x as x approaches 0?
From the left, it looks like it's 1.5, and from the right, it looks like 4. So it does not exist.
Correct. What's f of 2?
F of 2 does not exist.
What's the limit of f of x as we approach 2?
From the left, it's 2, and from the right, it's 2.
No, it's not 2. We're approaching 2 on the x-axis.
Yeah, it's
so
half.
What are we pointing to on the y-axis? It's a half.
Yes.
From the left? And what is it from the right?
A half.
So therefore, the limit is 1/2 as we approach
Correct.
2. So that's the answer to f is 1/2. Presuming that's 1/2, it looks like 1/2.
True.
F of 4?
2.
And the limit of f of x as we approach 4?
Infinity.
Good. I think you're getting the hang of it.
Yes, I definitely need to.
What's that?
Yes, I definitely need to because I have a quiz on this tomorrow.
No, I think you got it, especially if it's just figuring out the limits from the curve, from the graph.
Yes, it's just graphs. That's all it is.
In other words, you don't really need to do any of the algebraic solutions.
True, except the special one.
Yeah, except this one here. This is the only one that we were not able to answer just by looking at the graph. But you can kind of reason it out. In other words, 1 divided by 0 you know is going to be infinity. So the cosine of infinity can't really be anything because as the argument keeps getting bigger and bigger and bigger as you get to infinity, as you approach infinity, cosine keeps going -1, then 1, -1, then 1, and everything in between. Therefore, that limit doesn't exist. But like I said, of all the ones you showed me, this is the only one you really cannot figure out by just looking at that.
True.
Unless you understand that severe oscillation means the limit does not exist. And that's always the case whenever you see anything that looks like this. Just know that if there was a limit, they wouldn't show it to you like this because you can't figure it out, right? So the fact that you can't figure it out by looking at the graph almost means that it can't exist.
True.
Even if I were to magnify that and zoom in 1,000,000 times, wouldn't change anything. Still doesn't exist. Because it's
What type of,
What's that?
I was wondering what type of job would I be able to use this in specifically?
Amazingly, a lot. You're not the first person that's ever had a course in limits and then they say, well, what the heck good is that?
Yeah.
Well, believe it or not, it's really valuable. Let me just give you one example.
Okay.
If I want the limit under that graph, well, excuse me, if I want the area under that graph, do you know how to figure that out?
Not really.
No, geometry doesn't teach us. In other words, geometry teaches you how to deal with straight lines and circles, but not curved lines. Well, guess how we figure out the area under this curve? We're going to draw rectangles. Many as we can fit. Then we're going to add up the area of those rectangles. That's going to be the area under the curve. Now, as the width of each rectangle gets thinner and thinner and thinner, the accuracy gets better and better and better. In other words, if instead of those rectangles I put in a bunch more, in other words, let's call that H. So if I want the limit of these rectangles as H goes to 0, that actually gives me the exact area under the curve. And area under the curve is one of the classic problems of all time. Not only area under the curve, but area of the volume, or the volume of this thing. If I rotate it about the x-axis, I have a three-dimensional object, and if I wanted to know the volume, it's a limit problem. And it's only a limit problem. There's no other way to do it. For thousands of years, the only way that mathematicians had of figuring out the area here was to put as many rectangles as they could in there and figure the area of each rectangle and add them all up. And they came up with an approximate area. The problem is that when you put rectangles like this, there's always these little areas like this that's not under the curve, but it's part of the rectangle. If I draw a rectangle like that, well, that area that is under the curve, but it's not part of my rectangle. So the rectangles alone don't solve the problem. They approximate the area. But it turns out that if you put an infinite number of rectangles under this curve, in other words, make each one of them super thin, what are you doing? You're taking the limit of the sum of those rectangles as H goes to 0. So it's a limit problem.
Oh, okay, I see it now.
Okay? So that's one use, but another use is that limits have to do with rate of change. When you're talking differential calculus, you're talking about the slope of the tangent line, which is a rate of change. Well, instantaneous rate of change is all over life. There are literally 1,000,000 problems that deal with instantaneous rate of change. And the only way to figure out instantaneous rate of change is to make it a limit problem.
Okay.
Because rise is 0, run is 0. So if I want the instantaneous rate of change, I have no way of doing it unless I turn it into a limit problem. And then I can figure it out. And when you can solve for instantaneous rate of change, that's gigantic. There are so many things in the world that have to do with instantaneous rate of change. When you're driving down the road, your velocity is an instantaneous rate of change. It's the first derivative of position. So it has to do with velocity, it has to do with acceleration, has to do with any kind of rate of change that's instantaneous at all. Only calculus handles instantaneous rates of change. Algebra doesn't do it because you always end up with 0 over 0 and nobody knows what that is. That's indeterminate. But once you have calculus, which is all about limits, now you can figure out instantaneous rates of change. And that has enormous implications to real-life problems. So limits definitely have tons of real-life applications. The only thing that you're getting in your course now is the limit part, not the calculus part. But that's what it leads to. All calculus courses start out with limits because they're the most vital part of calculus. You couldn't do the rest of calculus without knowing how to do the limits.
True. So you have to build up the building blocks.
Exactly. It's the foundation of calculus is what you're studying right now. All of these limit questions, it's the foundation of calculus. And you'll understand that more next year when you take calculus. It's all about limits. So, all right, Taylor.
Thank you.
You're welcome. Talk to you next
Have a good
time.
night.
You too.
Sounds good.